be ahead of the wave in terms of what's the next hot research area, both for industry and academia. And he did all this amazing work in transportation and societal networks, and now he'll tell us about the next big thing.
Thank you, Dokian. Well, I will tell you certainly about self-programming networks. We'll see how that goes. This is work I'm doing with a number of people at Stanford. Notably, Mendel Rosenblum is a colleague. Operating systems, virtual machines. And then Dan Zheng is a senior research scientist, plus a number of students, of whom Vin Sachidananda is here. And so this is our group. It's a quest to make networks autonomous. Okay. And if you take your research topic and just add self-driving to it in front of it, like self-driving stable matchings, it just sounds better, okay? And so, you know, but more than that, no, it could be anything, you know. It's a self-driving doorknobs, which is better, okay? And so, our goal is to make networks autonomous, like, you know, that it should sense and monitor itself, and program and control itself, and be interactive, okay? So we think of our work as a combination of engineering and design. This means I will show you a demo at the end. And how to think of this? Well, let's think of self-driving cars. What does that mean? You can take a plain old car like a Volkswagen Touareg. If you add sense and control to it, it will become Stanley, the self-driving car. This is Sebastian, that's Stanley. The idea is by taking a car and adding LiDAR and you know, mapping and various other things, and controlling the steering and acceleration, you create the self-driving thing. Okay. So just so, we want to take a plain old data center. This is any data center that you can see, either large or small. Small would be 500 to 1,000, large would be 100,000 or a million. And they all look pretty much like this, what is called a leaf spine topology. So it's a multi-stage switching topology. These are all the servers. This is who wants to talk to each other, get some work done. And this is the switching interconnect fabric. Okay. And the data center supports some number of apps. And it processes workload coming from data related to these apps. That's really, you know, what it does. Okay. As far as our talk is concerned, that's yes.
Again, the usual systems question: what about the boundary? Where's the sheet metal here? Say this network might be serving mobile applications. I presume. So
the apps are all here. The sheet metal really is in the switches, and the servers.
Customer devices, end devices, customer end devices.
No, just think of just plain servers. Servers in a rack, and the racks are connected. Okay. Everything that happens is happening on top of it. Okay. So to this data center, we want to add some sensing and control and get ourselves a self-programming network. And so I will tell you exactly what we sense. So where's the sensing happening? And then what sort of problems come up for processing the sensed data? And then what sort of control does that lead us to exert? Okay? And the control can be a function of network state as well as operator policies. Okay? It's no different from, you know, self-driving cars. Cars have to respond to what's around them, but you may have some policies like, you know, don't go faster than 60 miles per hour, sort of thing, as an example. Or if you have particular cars, then don't go on some kind of roads. That's an example. Okay?
So what do the policies look like in the space of data center?
Don't let this app take more than X amount of bandwidth. Don't let these virtual machines of tenant A swamp and take up all the CPU cycles and starve the other guy, that sort of thing. So it's something to do with amount of compute, network bandwidth, and storage.
And are those typically like static and frozen, or are they?
It's usually some service level agreement that they achieve. If it's an internal data center, then it'll be just decided internally. Usually they're very dynamic. They're dynamic not in themselves, they're dynamic in that the enactment of this depends on the dynamic state of the network. Okay. So what does this get us? It gets us some new functionality not available in the plain old data center, like very accurate timestamping as a service, fine-grained network telemetry, and application network performance monitoring. I won't tell you about all of them, I will tell you about the first two. But that means you can now run some new applications that you could not run on the plain old data center. For example, a global distributed database like Spanner, this is Google's big, global database. What that means is it guarantees you consistency, what's called external consistency, strongest form, because it has accurate clocks across the globe. Okay? That's something you can run on this plain old data center now. You can't run on plain old data center, it doesn't have timestamping as a service, but if you enhance it, then you can run it. That's an example. Any consensus algorithms are usually designed from some sort of message passing foundation, but if you have accurate clocks, you can speed that up. That's an example. You have new things you can do. I already talked about this Monday last week. We had a one-day symposium, and I know the audience is not fully overlapping, but I don't want to revisit. The financial industry also cares a lot about accurate clocks. I think my talk's online in case you're interested. So I'm just going to stick with the two algorithms I promised, namely these two. Okay. So where's the sensing and control? Everything is for us going to happen with the network interface cards. This is what we're going to do primarily, not exclusively. Okay. And how that happens, I will tell you in a second. This is the work itself consists of thinking about NIC-based stuff and then having this query engine let us peek into this self-programming network. And we use a lot of data and machine learning to speed up hardware accelerate, and I'll show you that one more specifically. Okay. So what does sensing mean? The NICs mean? I will look at packets, data packets or probes. Probes are special packets that we insert. I will look at the time at which they're transmitted and the time at which they're received, and using these two timestamps, reconstruct how long the packet spent at each of the intermediate boxes. Okay? This is known as network tomography. It's a topic that's been around in the internet context, where it has achieved limited success just because the wire time in the internet is way bigger than the box time, so you end up, unfortunately, not being able to reconstruct accurately. So as soon as you see this, you can identify one problem. If these clocks aren't well synchronized, all of this approach is useless, right? Because the time taken in a data center to go from one side to the other is usually a few microseconds under no congestion, or like 10 microseconds. And under congestion, it's about 200 microseconds, half a millisecond. So it isn't really that much time. And if the clock synchronization is not good, this approach won't work. Okay, that's one thing. The second thing is to also note that there are details that I'm not going to cover, but let's assume we know the path. These are systems issues. There's ways of knowing this. Let's assume that. Okay. This has been implemented in different sort of layer 2 type networks and layer 3, and you can sort of use different things available there. If you look at what the system, so everything I've told you so far is just sensing and inferring. We're waiting on the smart NICs to come out in industry to do control, but they're coming out. Lots of companies are building smart NICs. But let me continue on telling you, I really want to tell you about the algorithms that go here. Okay? So the pipeline itself will look like there's a data center. There are timestamps taken from probes and data packets in just the way I told you. There's a clock synchronization step followed by a Q-length reconstruction step. This is solving this simultaneous noisy linear equations of breaking down by individual box from the total end-to-end time, and then also decomposing it by whose packets are in the queue and then I hope to have enough time to do a quick demo. So there's a few places it's been tried out, and some large ones and some homegrown, Stanford 1 gigabit per second testbed. It looks like this. This is the testbed. Okay. I won't tell you more about what are the servers and what the switches are. If you know networking, if you've done this sort of thing before, it'll be obvious. Otherwise, let's not worry about it. Okay. For the rest of the talk, I want to tell you about two algorithms, and that's it in this sort of demo. Okay. So let me start with the algorithm that presumes the existence of accurately synchronized clocks, and tell you how the reconstruction works. So let's first start with I have data packets only, no probes, okay, and I'm taking the timestamps of these data packets. Then this equation says the one-way delay, the time taken from transmit to receive, that is the one-way delay of each packet, equals the sum of the times it's spent at the individual boxes on the path, plus some propagation delay. And there's some noise here, because the wires are not all of equal length. These NICs don't apply timestamps exactly when they transmit the packets. There are other things called dark matter packets. These are packets not emitted by the switches, but the box switches are talking to each other to discover who's my neighbor. There's various things like this. Okay, and one of those packets get in front of one of our packets, and they may use other priorities, but in our Stanford testbed, they don't use other priorities, so they may induce small delays. So this is in the order of a few tens of nanoseconds. This is in microseconds to hundreds of microseconds. Okay, so it is indeed noise. Okay, are we okay with this? So we solve this using the Lasso algorithm, and I'm just going to write down for completeness what it is. Our criterion is to try and minimize. We want an estimate of the Q. This is a vector of Qs. I want an estimate of this such that it is minimum mean squared error estimate. So choose an estimate such that this is minimized for reasons that. So by the way, let me just read out what this equation is. In a millisecond of time, or in a certain amount of time, small time, which depends on the speed of the line, I will tell you how to pick that. One packet goes through, and you'll write this equation down. Okay. The set of Qs it visited is represented by this adjacency matrix. So the first row of the adjacency matrix picks the Qs in this vector of Qs that the first packet visited. Okay. And the second entry here is another packet going from some source to some other destination, and the set of Qs it visited, and so on. Okay? That's what this is. Sorry, I didn't say that before. Okay? Now, I want this minimum mean squared error estimate for reasons that have to do just the way the network topology is. That is a sort of multi-state switching topology. This matrix is always going to have less than full rank. So your solution is going to be underdetermined. The equations are underdetermined. But the way the congestion happens in these networks is it's sparse, and not all the entries of Q are going to be equally large. Okay, so there's just the fact that data centers have many, many paths means only some Qs you have lots of choice of paths. Okay? So I said a few things there. Okay. So we want to minimize this. We want to find an estimate of the Q that minimizes this. It is always the case in that with this criterion that the conditional expectation of Q given D is the best estimate. Okay. And one way to find this is to look at an equation of this type. So this is known, this is known, this is not known. And try and find the minimizing queue, okay? But since it's underdetermined and we're looking for a sparse solution, you add this L1 norm so that this whole thing is still convex, and you can solve this and find the minimizer and declare that to be the estimate, the mean square error estimate, okay? This is the Lasso algorithm. The algorithm that takes this cost function and determines the answer is the Lasso algorithm. Lasso algorithm is an algorithm that does it. Yes.
I'm a little confused. This is not, if you don't have unique paths, you also need to learn the mixture of packets going on the multi-path?
So for a single packet,
Yeah.
which is what each entry is, there's only one path.
You know the path. So, okay, you look at the...
One packet at a time. A flow's packets may have different paths. For each packet, there's only one path.
So you have a lasso in mind, right? What is that in this algorithm?
Straightforwardly, this is, it's a convex cost function. You will take the derivative, so,
That's the lasso.
That's right. The name Lasso comes from, there's a historical reason for that. That's right. Lasso is the name of the, it's an acronym. Okay? Okay, LASSO is in capitals.
So why are you regularizing towards 0?
Because we've empirically, the queues in a data center are sparsely occupied. Okay? Yes?
Typically, what's the dimension of D relative to Q?
I'll have some numbers in the thing later. Q is, if Q is 1,000, D is up to us because how much measurements we want to take. But D is in the order of 500 typically. When Q is 1,000, but for a big network, the numbers are bigger.
And is tuning lambda an issue here? Do you need to tune it dynamically? Or
Many values of lambda work. So it's not it's a fairly robust thing. Okay? They will give you slightly different answers, but for the non-zero ones, it's not appreciably different. Okay. So with that, let's see how it works. I'm going to start with NS3, which is a simulator, and then I'll get to the real networks. Okay. There is a queue that connects server 1 to top of the rack switch 0, and the blue line is the actual ground truth, and the red line is the fit solution from Lasso. The root mean square error is small, and it picks up small, all the small bumps and everything. So that's a fit. And then if you look at, sometimes it doesn't work well. And what's going on is that if I just have data packets, it is very badly underdetermined. Okay, that is, there's just not enough equations. So there's a misimputation going on. There's a queue here, in fact, but it's misimputed to being there, and so on. Okay. Maybe okay. This happens. There's nothing I can do. It's underdetermined. It depends on workload. Okay, it depends on how the traffic is flowing. Instead, if we add a mesh of queues, the mesh of probes, sorry, these are probes that we're emitting small packets. They get queued with the data packets. They're just picking up extra equations for us. Okay? And the network of probes is a random network. That is, each guy probes 10 or 15 other servers randomly. And the number 10 or 15 is held fixed, regardless of how many servers there are in total. Okay? It's a random graph. And then you still solve the same thing. You just have additional equations, and you can show that it solves the problem, meaning you'll determine all the queue sizes. Okay? In fact, even improve the errors. And the questions I want to answer is, what is being measured precisely? Why does it work? And how can this be speeded up? Because we find Lasso takes time. So in a data center, on a 10 or 40 gigabit per second link, you don't have more than a millisecond for reconstruction if it's real time on a 10 gig link and a quarter millisecond on a 40 gig link. So we need something that's going to help us speed up Lasso. So I'm going to tell us about these two things. Why does it work? Okay, so what is being reconstructed? The actual queue size on a 10 gigabit per second link, if you look at the queue at the time at which a packet is queued in or taken out, And that happens every 1.2 microseconds on a 10 gig link. So let's make it 1 microsecond. It'll look like this. If you take 1,000 of these readings, successive 1,000 readings, and average them, that is, add their values and divide by 1,000, you'll get this millisecond average. So in other words, it's just some filtered version of that guy. Okay? And so we're going to reconstruct this. Not only is that easier to reconstruct, that is, you know, switches will give you things that look like this, but the amount of data here is just huge. Okay? And so now just digging into that a little bit more, if I have a 10 gigabits per second sample, if I have a 10 gigabit per second link, and I sample the queue 1 microsecond, I get this. And when I look at the 1 millisecond average, I get what I showed you. That is what's happening in the network. What we're doing, on the other hand, is I have a mesh of probes, and they're probing at some frequency. In this talk, I won't tell you how to determine the frequency at which to probe. Not enough time, but we're going to probe them at some frequency. So literally what's going on in this example is, for every millisecond, I launch a bunch of probes from different servers destined for, you know, other servers. And I look at the time that they spent and call that milliseconds worth of data and ship it to this algorithm to go reconstruct. And then that'll be 1 point in this graph. Then go to the next millisecond, repeat this. Are you okay with this? That's what's happening. And that's what this is. And we take the probes data, estimate it, and then we're going to say that what we get here is an estimate of that. Right? That's what we're doing.
So can I ask a quick question? So the one on the left at the bottom, you just make observations and average them. And you made observations of queue times or queue lengths and average them. So that's not Lasso, estimated with Lasso.
No. That is just the so I took the queue size process and just took a moving window average, or you know, just non-overlapping windows of. I applied an operation to this thing to get this. This is not Lasso. This is just what I'm saying. We're going to reconstruct this.
Just observe. And so okay. So when you estimate something with Lasso, you don't observe the queue lengths.
No.
You just observe the time from origin to destination of the package.
Right.
But on the left, you observe the queue lengths.
That's right. I'm trying to give a theoretical reason. No, I'm not. I'm saying this is what we're doing.
Yeah.
We're claiming that this is going to estimate that. I'm not observing that. But I have to prove to you that this is in fact going to estimate that, right?
So this is some simulated system. You pretend that you can observe the queue lengths.
Yeah. Or I can measure it in reality.
So that's the
Just for, right. It's the ground truth.
I understand it's the ground truth, but you're trying to develop, I'm trying to see what you're trying to do. You're trying to develop a system where you don't observe
That's
the
right.
queue lengths.
Right. So the first thing I want to do is, why does this microsecond average and millisecond, what's going on here? Okay, so is this a sensible thing to do? So if you look at this thing in the frequency domain, meaning you take the autocorrelation function of the 1 microsecond queue size process, take the Fourier transform, it's two-sided, but it's an even function, so you plot on one side, you'll get this. This is how much power is in what frequency, okay? And this is for the 1 microsecond sample thing. And if I superimpose the 1 millisecond average, it is exactly the same. This shouldn't be, this is expected to be, okay? And there are no frequencies beyond 500 kilohertz because they're all averaged out. Okay, this is just what it should be. But what we're doing is you can take a moving average of 1,000 points, thing, and then downsample it. So you heard a little bit of this flavor of things in the previous speaker's talk, okay? And that's what this is doing. And if you look at what's happening in the frequency domain, you're going to get this aliased thing, and you're going to pick one of them, okay? That is effectively what this, 1 millisecond average is doing. But the point of this graph is, what is the power captured in this blue signal we're interested in? How much of the original thing is still captured, okay? So notice that the y-axis is log scale. The 1 millisecond average guy has in excess of 97% of the power, okay? So the 1 microsecond guy and the 1 millisecond guy are pretty much identical except for 2.5 to 3% power, okay? That's how much noise. So what's been removed is just a very insignificant amount, okay? So therefore, it's the right thing to reconstruct. But this is true across a variety of different networks, different packet sizes and various things, okay? So if I take a 1 gigabit per second network, a 10 and so 1, 10 and a 40, then, and I say I'm looking to see what fraction of power I want left behind. So that's 97% there, okay, 97.5 actually. Then it tells you what is the right interval to average over, okay? Which means for the system we're developing, what interval of probes are you going to, solve Lasso for? And the number for a 1 gig line is 10 milliseconds. For a 10 gig line is 1 millisecond and so on, okay? So that is the interval over which you'll have to keep solving Lasso. Are you okay with this? Yes.
I think back in your definition of probe, you had an ACNAC acknowledgement included. What are the implications of acknowledgements not being of failed probe transmissions?
Good question. So there'll be a blank entry. You can either choose to include it or not.
Both ends.
Yeah. So you can just say I lost a packet. It's very helpful to include that information. That is some buffer overflowed. Okay, that's very useful to include.
Especially probes.
Yeah. No, but even data packets for that matter. They're indistinguishable from the purpose of the algorithm. And there's probes have a more easy way of getting through because they're shorter. So it's harder to drop a probe than to drop a data packet. Okay. Let me continue because now I'm definitely behind time. So one of the things that we ran into was just this Lasso algorithm was taking time to solve and doesn't scale as well. So it's natural to ask the question. Even if I take the output of Lasso for multiple pairs of, so think of this as a map. Lasso is a map that given D is going to give us a Q. So for a given D, I get a Q and I have multiple DQ pairs. So if I take all these DQ pairs and go train a neural network, might that help me to speed up the solution? Everybody okay with this? So you can either solve Lasso or you can teach neural network solve it. The weights are such. And since the governing equation is a linear equation with noise, there's some hope that it's not going to be horrible. So that's what we did. So we took Lasso as a black box algorithm, although it isn't. And then we trained a neural network just to see what acceleration one can get. And I'm not going, everybody knows what ReLUs are, so I'm just, this is end of second decade 20, everybody knows this. I'm not going to spend time explaining this, okay? But the important thing is it's just a one hidden layer. It's not, this is a shallow neural network, okay? We want to know what's the quality of reconstruction by the neural network. How well is it learning Lasso itself, and how well does it learn ground truth when you can supply it? What is the speed up that you get? That's the more important thing, okay, from our perspective. And here's the answer. So first thing is the quality. The root mean squared error. So I think someone asked what are the sizes. So in this system where there are 256 servers, there's one more coming down here. How many Qs, how many paths, and how many Ds, okay? So let's focus on this one. What this is saying is the root mean squared error for Lasso alone versus a neural network trained with ground truth, not with Lasso, or trained with Lasso. It's pretty good performance. So just to give you an idea of what that means, why am I declaring it's good? A 1500 byte packet is the size of a TCP packet. So this is about 3.5 packets. So this is like super small, errors. And so you can now, 1500 byte packets is one packet, okay? Now here's the more interesting thing from our perspective. Even if you use sparse versions of Lasso, every millisecond's worth of data takes this amount of time for even modest-sized data centers or subnets, whereas this one is like really fast. It allows you to do things like batching. And we took a pretty straightforward GPU. That's something that comes with the virtual reality system, Vive. So this isn't even optimized GPU. So, but you get an order of magnitude comparison. So it's like it's 5 or 10,000x faster. Okay.
So why wouldn't you use the neural network in the second column?
Why wouldn't you use the?
Why wouldn't you use the neural network in the second column directly? Like,
No, this is the point about you don't have ground truth.
But like this is, I mean, presumably you just collected data for some time and.
No, but you don't have ground truth. You may know the end-to-end data. You don't know the switch sizes, right? Q size in the switch.
So it's not possible to measure it even.
No, not for these many Qs, no. Right. So, okay. That connects up a few things, right? So now, quickly, let me tell you this, okay? Okay, and I know there's a break coming, so what I'll do is I'll offer to show you a demo during break time, okay? So clock synchronization is just a well-known like it's been a problem around. We've all known about this distributed system people. We just like have to deal with things how to just synchronize and whether it's databases or now distributed ledgers or various other things, you have to synchronize clocks. Or if you have synchronized clocks, then life is much better. I'll leave this for the paper reading. So the point is either you have software solutions that are inaccurate or hardware-assisted solutions that are pretty expensive. What you would like is a software solution that's accurate, okay? And that's what we're going to look at. So almost all clock synchronization algorithms between a pair of servers A and B, who each have their clocks marking time as T sub A and T sub B, which are off from the actual time by some unknown discrepancies, will exchange probes. Okay, so you get 4 timestamps. You use these 4 timestamps as follows. Receive time of a probe, it always equals the actual transmit time plus some whatever delay there was. And if you write it in terms of the timestamps, less the unknown discrepancies, is an equation. If you put the unknowns on one side, you'll get this equation, and if I remove this positive quantity, I will get a bound. From the probe in the reverse direction, I will get a lower bound with the other 2 timestamps. If you plot the bounds, this is how it's going to look. So this is from the Google 40G testbed. What this is the time according to clock A is on the x-axis. The unknown discrepancy for which we have bounds, each blue dot is an upper bound, each green dot is a lower bound. Ignore these guys in the middle for a second. This thick blue line and thick green line are the shortest time to go from A to B and B to A respectively. So this is the one-way, this is the round trip time, this gap. Okay. Assuming the path is symmetric in the sense that forwards time and backwards time are equal or nearly equal, you're left with finding this middle red line. And suppose you find it. It's still not telling you about the dots in between. I'll come to that, okay? If you do, then what you can say is, when the clock at server A said 0, the clock at server B said, whatever, 93 point something, okay? Minus. The clock at server B is running slower by that amount, okay? And 2 minutes later, he's fallen further behind. That's because the 2 clocks have a relative frequency difference indicated by the slope of this line. In fact, the relative frequency difference, that B is ticking slower than A by this amount of microseconds per second. Okay, are you okay with this? So the 2 clocks are perfectly synchronized. The slope and intercept should be both 0. Okay? So now, most schemes just try and set the offset, correct the offset, determine and correct the offset. But as you can see, the frequency is just not good from, the clock frequencies are off. This is actually a mild form of drift. This is from different pairs of servers, or whether in the same rack or separated by one level of spine switch or 2 and so on. And they all have different slopes and intercepts, okay? Now, just to tell you a little bit about the points in the middle, they're noisy NIC timestamps. So sometimes this network interface card's timestamp after the packet's gone. So you artificially get a small propagation time, smaller than possible propagation time. Okay. So, right, everybody okay with this? So in this room, if I say support vector machines, of course, because you classify, there's blue dots and there's labeled, okay, data, and you just have to find a separating hyperplane, and you will use a soft margin support vector machine, so it's not to worry about these guys, okay. But this is empirically showing you that often the clocks are off by 5 to 10 microseconds per second relative to one another, these pairs of clocks. And they can be as badly drifting from, there's some pair that's going apart as 30 microseconds per second. Okay. Okay, so from now on, so this is, if you look over longer periods of time, the clock's frequency difference is not linearly related there. Some clock is ticking slower and slower and slower. This happens when they get hot. And they get hot when they pump a lot of packets. So we can deliberately make this happen, okay, if we want. We've made it happen. We've even taken blow dryers and made them hotter, okay? So you can do these things, okay? So what we do is we synchronize everything in 2-second chunks, and at that 2-second interval, the frequency difference isn't present. I mean, it doesn't kick in. So in another minute or so, I'll tell you about this, finding this middle red line. Okay, this is the algorithm part, so there are 3 things to say. First is support vector machines, like I said. It'll give you the 2 support vectors and the separating hyperplane. As you can see at this level of zoom, it's not really a good fit because this noisy stuff is like interfering with its performance, right? But already you can synchronize the clocks to about 300 to 400 nanoseconds of accuracy. Now, if we could find a way to send a probe and get a certificate that this was a pure probe, that it encountered no noise, no queuing delays, nothing, life would be great. Okay, so how do we do that? Because this is networking data, you can actually do it. So think of each probe as actually 2 probes sent back to back. They happen to be separated by some amount in their transmit timestamps. In this example, they're separated by 10 microseconds. It could be whatever the number is. Then on the outside, on the reception side, 3 things can happen. Either they come separated by a lot, more than they went in which case, second guy got delayed, regardless of whether the first guy got delayed or not. Second guy got delayed more, so that's why it's separated. So we'll throw away all those, or it shrunk, then we'll throw away all those. Then they come apart almost equal, meaning up to 50 nanosecond type guard band, okay? We will keep those. Because it'd be a miracle if the network somehow managed to give both of them exactly the same delay. So the most likely explanation is they got 0 queuing delay. Anything positive for one to match that exactly for the other network has to be pretty devious, okay? The same goes for noise, timestamp noise. So if you take that data we had before and apply that filter, you will lose 90% of the bad stuff and keep 90% of the good stuff, okay? Now this already leads to an improvement of a factor of 4 in the accuracy of clocks, okay? So finally, this is like what else is there left to exploit? Clocks have been synchronized pairwise typically, over a tree. That's typically how NTP functions, okay? But if you observe that clock synchronization has to be not just reflexive and symmetric, that is, I have to synchronize with myself. If I'm synchronized with B, B has to synchronize with me, it has to be transitive, then obviously you'll get this extra final thing where 2 clocks are mutually synchronized and they think they're off by 15 minutes, that's the offset. And then B and C are mutually synchronized and B says if I'm at 10:15, C must be at 10:05. And finally, C says if I'm at 10:05, A must be at 9:50. So by going around the loop, they detect that they're not well synchronized. And then the question is, how do you apportion this? How do you correct the error? And there's various ways. And when you put all the loops in this probe graph together, you can correct it. There's an algorithm for doing it, okay? And the important thing is as you increase the number of other servers you're probing, the number of loops will increase, so this network effect will help you. The mean error will come down, but more importantly, the 99th percentile is going to come down a lot more. It is just difficult for you to have outliers when you go around these loops and start getting people to agree, okay? So that's the algorithm. There's a whole bunch, there's analysis and stuff. There's a whole bunch of other things. It works well at high load. It's still under 40 nanosecond type accuracy at high load. This is for 128 servers. Okay. I don't have time for demo, so I'll stop. I do have it here. Okay, if you want, I'm happy to talk to you. Thank you.
How long does the demo take to show?
Oh, it's not, I have loaded it already. So, what am I going to show? Friendly chair. Okay. Thank you. Okay, so I told you there's a dashboard. This is what it looks like. So each gray box there is a server, and each green thing is a top of the rack. So these are all servers. There's 16 servers per top of the rack switch. There are 8 top of the rack, so 128 servers. Ignore the orange guys. That's to prove the accuracy of clock sync. We're not going to worry about that. These guys are connected to each other through a layer of spine switches, blue spine switches. These are alerts. Since you're taking a NIC-based approach, it's very easy. So the number one indication that your network has a problem is that some packet had to be retransmitted. And the number 2 problem, and more severe, is that some TCP source timed out. So since both are easier for a NIC to detect, those alerts can be raised. Okay? So the demo itself is, we've taken all these timestamps, sender, receiver, NICs. The clocks have been synchronized. And this is from the basement data center at Stanford. Okay? So you can reconstruct the exact way in which the files got transferred. That's a request going from, so there's a so-called in-cost load, which, if you know networking, it means this guy is requesting 3 other servers to send files simultaneously. This happens with Facebook, when you go and you download your Facebook page. Your web server is requesting this simultaneously. So this switch is going to get overloaded and drop packets. Okay, so it's a particularly bad workload from a congestion perspective. The clock here, if you can see, it's ticking at microseconds. Okay, so microseconds and milliseconds. Microseconds, milliseconds, seconds, like that. So you can really observe this, very fine grain. Everything is reconstructed. So other guys are doing file transfers, and you can accelerate like a video. You can just watch. Nothing happens at the level of microseconds. Data centers are not that fun to look at. They're not exactly, there's nothing happening. You have to wait like for a long time before something happens, okay? So you can just fast forward this, or you can raise alerts, only go look at times of alert. Or you can sort of, if you're impatient, you can even do that, okay? And so you can sort of, this is all, what I'm making is this is all reconstructed. I don't have any switch-based telemetry, nothing, right? So it's like algorithms. The reason we're all here. Right? So, and then it can get very cluttery to do all this sort of viewing. So you can sort of say, I don't want to look at everything. Just show me the stuff that goes through that switch. And only that switch, meaning I don't want to, so just hide everything away. So you can sort of build these things. And I think this makes life very easy for those who want to debug stuff. So if any of you have played with NS3 or NS2, it's a painful thing. Okay, no grad student should be suffering anymore. Okay, you got to look at this. Okay, so and then this is a view that says at a given time, what does a subnet or a network look like, right? The dual view would be if I pick a link or a location in the network like this and show me what the congestion of that link looks like. So this is the reconstructed queue size. This is the reconstructed link utilization. So whenever the link hits 100% utilization, it overshoots into this queue, right? And that thing is resident in my laptop, so it's all in the cloud. So this is a great boon for having, Wi-Fi connectivity and so on. But if I zoom in, this is exactly the same figures as above, but broken down by whose packets are on the link or whose packets are in the queue. This is the attribution, okay? So now we can say, well, my traffic is getting screwed over by those guys, okay? Shut them down like this, okay? So that's the idea of this dashboard. There's a few more things to say, but I will, well, there's actually, let me just tell you one thing about the alerts and we're done. So I picked, let's say, this circle, that's a flow that was transmitting a file from here to here on that path and it timed out. Okay? So just this algorithm that we have has determined that this is the culprit link, that's the link which caused its packets to be dropped. Okay? Because we can actually reconstruct, right? So as someone who wants to go figure out what happened, you can look at that link, and this is the reconstructed queue size in total queue size in gray. Our flow was just a small amount of bytes. It got stopped here, the pink one, and then nothing happened. Pink was not transmitting for 200 milliseconds, and then started again. Okay? So he's an innocent sort of guy who got sideswiped by all this huge amount of background traffic. This is one of those things you can figure out whether you caused the congestion or if somebody else hurt you, right? So anyway, well, thanks a lot for your patience, and thank you.
I guess maybe in the interest of the break, we can take questions offline.